Welcome all of you for the week 9 live session of Power System Engineering NPTEL course. I am Gagan Meena and I am currently doing PhD at Electrical Engineering Department, IIT Bombay, and my area is Power System Engineering. So this will be the agenda for today's session. So we will start with a brief overview of week 9 and then we will discuss some questions related to week 9, which will help you to solve the assignments. So this is the deadline for assignment 9, March 27th. So please submit the assignment before the deadline. And you can find the recordings, the links for the recordings of live session in the portal. There is a link for Google Drive where you can find all the PPTs as well as the link for the recordings. Okay, let us start with the overview of week 9. So in week 9 we basically discussed, actually we started in week 8 itself. The discussion was on the application of capacitors in the distribution system. So both two types of capacitors, that capacitors can be used in two different configurations, one in series or one in shunt. So suppose we have a line. Let us consider this line between two nodes, node 1 and 2 or bus 1 and 2. So if we connect the capacitor, hello Deepak,
Good afternoon, sir.
am I audible?
Yes, sir. You are audible. Good afternoon, sir.
Good afternoon, how are you?
Sir, I am fine.
Okay, so I just started the session. We are starting with the overview of week 9. So we will start with a simple, brief, quick overview of week 9, then we will discuss the questions. Okay.
Yes, sir.
So I was saying that we started with the week 8 itself. In week 8, the last two lectures or 1.5 lectures were on this application of capacitor in capacitance in distribution system. I was saying that we can use capacitance in two different configuration. One in series or second one is in shunt. So we can have this. So each line that we have, distribution line, it is having R and X. And if we add one capacitor in series with this line, then it is R plus J X minus XC. So now what will happen to the impedance? Will it increase or decrease? So initially the impedance was R plus Jx, and the new with series capacitance, let me write series as SE series. So this is R plus Jx L XL minus XC. So which one is, what is the relationship between this Z and ZSC? So equal, greater or less?
Sir, Z is less than. No, Z is greater than ZSE.
Yes, correct. So ZSC, after using the series capacitor, this impedance reduces because XL minus XC we are having. So if both are equal, XL is equals to XC, and there is only resistance, then it will be a case of series resonance. There will be no reactive power. Whatever reactive power is required by the load as well as the reactive power losses which are happening in the line, both are being catered by the capacitor itself. That is why this value of capacitor will result in only active power in the in the distribution line. So active power losses and load will also be consuming active power, and the reactive power which will be supplied by the capacitor, the series capacitor. And if XC is greater than XL, then it becomes R minus J. So then it becomes negative. This XL minus XC becomes negative. So it is overcompensation. So we are having capacitance which is even more than the required necessary. So because of that, what will happen? This, if the voltage here is Vs and this is Vr, then this Vr will be more, because it will. We have seen that formula for voltage drop last time. Do you remember? What was the formula? Approximate formula for voltage drop? Is this correct?
Yes, sir.
Yeah, so we discussed this. Suppose now here if X becomes, so here X without capacitance is XL, but now it is XL minus XC, and this is negative. So this will be IR cos theta minus IX sin theta. Or X will become negative, but actually, so there will be a voltage rise instead of voltage drop of around this much. So we can derive the exact using the same phasor diagram which we had last time. So we'll see that this was without capacitor. So first, suppose we discussed the two methods for power flow. Right? One was using the voltage flat start. Second was using losses. This was linear. Second one was non-linear. Because here we have both voltage and magnitude and angle information for voltage. So, and second one was we assume only the voltage angle. Sorry, voltage magnitude, not the angle. And for each line we make the equivalent circuit. So for first branch this will be the equivalent, and let us say this is P2 plus JQ2 and this is P3 plus JQ3. So equivalent for this will be summation of all P's beyond this branch. So it will be P2 plus P3 plus losses in this branch. Similarly, Q2 plus Q3 plus Q loss. Okay. Now if we connect one capacitor here, a shunt capacitor, so this was series. So what is the use of series capacitance? It is the main purpose of series capacitance is to increase the voltage magnitude of the nodes. So suppose this is node 1 and 2, So if it is connected to this node 2, it will increase the voltage at only node 2 to increase the voltage at each node. This is the primary objective of using a series capacitance. So if now what will happen? So if voltage increases at that bus, then since power losses are inversely proportional to voltage square, so if voltage increases, power loss reduces. So this is secondary effect. But main thing that will happen is it will increase the voltage at that bus, and because of that, power losses also reduce in the branches. And so this is for series. And for shunt, the main use of shunt capacitance, can you tell? Do you remember? So this is to increase voltage. The shunt one is for,
Sir, to supply the reactive power.
yeah. In both the cases, capacitance is supplying the reactive power. It is providing lagging watts, but
Power factor improvement.
power factor improvement is there. It is a side effect, but main thing that we want to do is to reduce the power losses.
Okay.
So its main objective is to reduce power loss. Because capacitor is supplying, suppose here branch current was I1 and this is I2, and I2 is both are complex numbers. So I1 will be, so here if it is providing QC amount of reactive power supplying, so what will be the equivalent now? This is without capacitor. So with capacitance, now we have to incorporate this also. P will remain same because we assume that capacitor is lossless. It is not consuming any active power. Q will change. So it will be Q2 plus Q3 minus QC plus Q loss. So now this is coming with a negative sign. So this will reduce the reactive power requirement. Suppose here the branch current was I1 and here one kept here, not here. So this is the capacitor. It is providing current IC. So this current is, let's say, I1 real part plus, if lagging load is there, then it is minus I1 imaginary part minus JI1. But now this capacitor is also providing a current here. So it will result in plus JIC. So now it is I1 real minus J I1 imaginary minus IC. So now this current, the total reactive component of the current which is required from the substation, which was being provided by the substation, it reduces. So if we say that current before without capacitor was this one, I1R plus J, not plus, minus, considering a lagging load, it was minus I1 imaginary, and with capacitance it is I1R minus J I1 imaginary minus IC. So which of these current is smaller? So what magnitude of IWC and magnitude of IC? What is the relationship between the two? Which one is smaller?
So I think smaller is IWC.
Which one? IC is smaller, yes, correct. Because this reactive power current requirement is being supplied partly by the capacitor current. So because of this I1 branch current, which is IC, I1 WC and IC. So I1C reduces the current drawn from the substation. It reduces, and if it reduces, then the power loss will also reduce. And if current drawn is reducing, so little bit there will also be a voltage improvement.
Yes, sir. But sir, in series, how we will connect the capacitor of
How
transmission line?
how we will connect the capacitor?
Yes, sir.
So if there is existing line, then we have to in between. So suppose it was like this: bus one, bus two, bus three. So now we need to separate this out. So it is a bus one, two, and three. This was earlier before series capacitors. Now suppose I want to add one series capacitance at bus 2. So now it is 2. I will add the capacitance here, and then I will connect this line. So this is 2 dash. So generally in distribution system we don't use capacitor, series capacitor much. It is mainly used in transmission system. So in transmission system even the requirement of capacitance is also very large. So it is there in the substation. So we create another bus. So in between these two lines, this series capacitor will be added in series. Okay, this will happen in the substation.
Okay, sir.
Or if you want to add
Sir,
in
will
existing,
we?
if you want to add in existing line, then we have to create one small substation there. We need to break that line and insert this capacitor.
Okay. Yes, sir. So we cannot insert in overhead like we have to make a substation.
Yeah, directly we cannot do that because it is in series. We have to break.
Yes, sir.
If in existing line I want to add, then I need to break the line
Yes,
first.
sir.
Then add the series, the capacitor, and then again connect it.
But sir, so large heavy voltage, they
Yes.
can stay with that.
Yes. First of all, the line will be de-energized. Whenever such things are done, first of all, we have to de-energize the line. There will be no current, the charging current or anything in the line. So we can operate it. We can make that, create a new substation there, and then again charge the line and start the operation. So such a high voltage is there, so we have to take all the safety measures, precautions. So before doing any kind of maintenance and anything, so line is always de-energized. First the circuit breaker will be opened, isolators are opened, then ground, both the side of the lines are grounded, and then whatever charge is there, it will go through the ground. Then the the maintenance work is carried out, or anything, whatever upgradation is required, that is done.
Yes, sir.
Okay, so I was saying is this was we were talking about the shunt capacitor. So here, because of capacitance, the current magnitude which is drawn from the substation, that is reducing, and as a result the power loss also reduces. And because current drawn is being reduced, the voltage drop also reduces a little bit. and as a result the voltage profile improves, or voltage regulation is improved. But the main purpose of shunt capacitor is not to increase voltage, it is to reduce the power losses. That is a secondary objective. The voltage lit- improvement is there little bit, but not that much as compared to the series. In series capacitance, there will be a lot of increase in voltage as compared to shunt. So here also one difference is both these this shunt adding a capacitance is a local phenomena. Suppose we are adding a capacitor here at bus 2. Let's say, let me move to next page. So if we have 4 buses, let's say, and we are adding a capacitor here. This is branch current I1, this is I2, this is I3, let's say, this is fifth, I4. And we have load at each of these, P2 plus JQ2, P3 plus JQ3, this is P4 plus JQ4, and this is P5 plus JQ5. Now if we write the equivalent, if we use a method to and write the equivalent model, then what will be the equivalent load here? Say P2 dash. What will be P2 dash?
So P2 plus P3 plus P4 plus P5
Yes, P2 plus P3 plus P4 plus P5 plus losses.
plus losses.
Let us
Yes.
assume that this is first iteration, so it will be 0. What will be Q2 dash?
So Q2 plus Q3 plus Q4 plus Q5 plus Q loss
Only this much? Anything else?
minus QC.
Yes, good. So we are seeing the effect here. So here also the Q2 dash is seeing this minus QC. If we write Q3 dash, then only this term will be not there, but rest all the terms will be there. So Q3 plus Q4 plus Q5 minus QC plus Q loss. Similarly, Q4 will be Q4 plus Q5 minus QC plus Q loss. If we see Q5, then Q5 is simply Q5 plus QL. Will there be no QL?
So QC.
No QC, na? Because even sorry, here also QC will not be there. No QC here. Because QC is only up to this third node. If we are drawing the branch equivalent model for this branch, then we see the sum of all the power beyond Q beyond this branch. There is only Q4 and Q5. QC is not there. So we see that when the capacitor is added at bus 3, its effect is seen only at bus 2 and 3, not on the buses beyond the bus to which it is connected. Only the buses before that are affected in that bus. And those the buses which are nearest to it will be more impact. So this IC is being provided by this capacitor here. So maximum effect we will see at voltage at bus 2 because some current goes to this load. Then here the current will be further reduced. So the reduction in current power losses will be more in branch 2 as compared to branch 1 because of this capacitor. So as you move away from that particular bus where the capacitor is connected, the reduction in power losses and its effect, subsequent effects, that will keep on reducing. Okay, is this fine? Clear?
Yes, sir.
So we saw capacitor. I was saying that voltage drop for series capacitor. Last time we saw that it is IR cos theta plus IR sin theta. But now, sorry, IX. But now with capacitor, this is without capacitor. With capacitor, this X is not X. This X is XL minus, or if we write it like this, minus XC minus XL sin theta. So if XC is more than XL, then this second term is negative, which means that there is a voltage rise instead of voltage drop. Okay, correct. So it might happen that the series capacitor which is connected in the line is designed for normal levels, normal loading. But if load increases, then that value of capacitor may be resulting in overcompensation. And because of that, this can happen. So there can be voltage rise. So it will result in voltage boost at this particular bus. So if a capacitor, series capacitor is connected here, bus 1, 2, 3, then voltage 3 can be more than V2 because of this overcompensation. If XC is greater than XL, this is XC and there is XL also. This is R plus JXL, R minus JXL plus XC. J and R minus JXL. So if XC is greater than XL, then there will be voltage increase. Because we see, suppose if we draw the phasor diagram, so this is VR, and if we have a lagging load, this is R into IR, this is IR, this is I into IR. If it is a lagging load, so this will be Z and this will be Vs finally. This will be X into JIX. Okay. R. This will be I into Z. This is without capacitor. But if we add the capacitor, then what will happen? This phasor, because now X is positive here. But if X, which is XC, or let's say XL minus XC, no? XL minus XC, and if XC is more than XL, then this becomes negative. So this phasor will actually become like this. It will become like this. And you will see Vs will be now Okay. So you can clearly see here, VR is greater than VS here, right? This is XL minus XC, which is negative. So this one is without capacitor, without series capacitor, and this is with capacitor.
Sir, in this case, IR will lead to VR.
So if the load is lagging, then so I am saying here, we are saying here that suppose this is the line, this is R, this is X, and we have one capacitor here. This is load. Load is drawing some P plus JQ. So that IR, load current. This is lagging. So this is some I, some real, let's say IR, real plus 9, because it is lagging. So it will be minus J IR imaginary. Okay, load current is lagging. This is so I am saying load current is lagging. So that's why I've shown load current as lagging. Let me explain it here again. So, so there can be two cases. Load can be either leading or lagging. So what I have shown here is for lagging load. This is minus JXC, JXL, and this is R. So here we are assuming that it is a lagging load. So this is case 1. Okay, so this is VR and IR because it is lagging. So this is R into IR. Okay, because of this. Because IR is lagging, so it will R into IR is there is no complex, it is simply multiplied. So it will just scale the phasor. So it is in the same direction, only scaled. Then we have to add JXL. JXL is 90 degree. So JXL. This is JXL. Okay. Then minus JXC. So minus JXC will come here. It will be minus JXC into IR. So this is minus JXC into IR. This is JXL into IR. Don't look. Okay. Now this is negative, this is positive, so overall it will be somewhere here reduced. Let's say so. This is, let's say this is J IR into XL minus XC, assuming that XL is greater than XC here.
Yes, sir, clear.
Yeah, and if XC is greater than XL, which I showed, if XC is greater than XL, then let's say
It will
this
be
was,
clockwise.
yeah, so this was XL, but XC is much larger, so it is somewhere here. It is like this. So resultant will also will come here somewhere here. Then Vs will be this. This will be Vs in that case. This becomes Vs. But if the load is leading, then it is VR, IR. This is IR, leading load, IR. Then this will be XL. This is minus XC, minus J I into XC. And if this is larger, this is big, XC is more than XL, then it will be like this. And Vs will be here. Okay. Correct. Yeah, so this will happen because of the capacitor, series capacitor. So if XC is more than XL, then it will lead to voltage rise. This is overcompensation. Okay. Then let us draw. This was for series. Let us draw the phasor diagram for. So here we see the current is same. There is no change in the current. Because there is no change in the current and voltage is reducing, sorry, voltage is increasing because of this capacitor. This capacitor is increasing the voltage. So if this was 1 per unit, this was 0.95 without capacitor. With capacitor, let's say this is 0.97. So in second case, the current will be, so voltage drop is less here. Because this is adding, we saw that in the phasor diagram. So up to here there is a voltage, same voltage drop, but because of this capacitor, this voltage increases. Because instead of creating a voltage, further voltage drop, it is actually increasing the voltage. That is why in the voltage drop formula we are having this Y IR cos theta. Instead of uh, plus, here we are having a negative. That means there is voltage rise instead of drop. Now how much rise will be there, it depends upon the value of this C, XC and XL. The value of XC will determine that. Then, yeah, so we're talking about this shunt capacitor. So if you have a shunt capacitor here, the bus 1, bus 2, it's a current, let's say it's a lagging load. This is VR, this is VS, this is VR. It's a lagging load, so it is IR. This angle is theta. So this is RIR plus IXL, JIXL, and this becomes VS. Now, if you have a capacitor also here, which is supplying a current, now it is with respect to VR. IC is lagging or leading?
So leading.
Yes, so this is VR. IR is still here, lagging at an angle theta. But we have IC here, leading. This makes us I'll give the different color. Okay. So IC is smaller. Okay. So this is same R into IR. Then this is JI into XL. This will be sorry, like this. Let, first of all, we have to calculate the current, actual current because of this capacitor. So this IC is now this because of capacitor. This is not I. This is I dash. So this we have to calculate. So we have to add this capacitor current here. So now this becomes the I dash. So initially the angle was this theta. Theta 1, and with capacitor it results in theta 2. So now current is this. Current is actually this. So R, this becomes R into IR. I dash, sorry. R into I dash. And this becomes J X into I dash. And this becomes VS. VS dash. This was VS. So this is the angle theta due to. Now theta 1, which one is greater? Theta 1 or theta 2?
So theta 1.
Yes, theta 1 is greater because of adding the shunt capacitor. The theta is reducing. Phase angle difference is reducing, so what cos theta will increase. That is, once power factor is improving. But here this is not happening. Here current is same because it is in series. Whatever current is flowing here, same current is flowing through the series capacitor also. And the magnitude will change. So here the power factor is not much change in power factor as compared to this shunt one. So in this case, we are changing the impedance, but here we are not changing the impedance of the line. We are actually changing the current which is flowing through the line. Okay. Capacitor is providing that current, the active component. That is why here power factor is reducing. So one thing, you can see one question also here. So initially it was drawing some Q reactive power, and load is drawing QL, load plus PL. active and reactive items. And this capacitor is providing QC reactive power, no active power. So from substation we are drawing P, so you have to supply this PL, and so Q net, which is required Q. Q will be actually QL minus QC. So without capacitor, this has to supply entire Q. But now because part of it is being supplied by the capacitor, so it has to supply less reactive power. So it is QL minus QC. If you draw the power triangle, this is P load, PL, and initially it was this QL. This is QL. So this is theta without capacitor. Now because of adding capacitor, there is only this is net Q, which is Q is QL minus QC. So this much is QC. So this much reactive power is being provided by the capacitor, supplied by the capacitor, and that is why this power factor is improving. So this is S1 and this is S2. So what is so PL is same in both the cases. So can you tell what is QL in terms of PL and theta? How much is this QL by PL? Yes, Deepak. This is PL tan theta and QC, not QC, Q. Q becomes PL tan theta C. So then QC is equals to Q minus QL. So PL is same, tan theta C minus tan theta. Okay, is this clear? QL. C theta. So QC is P tan theta QL minus Q. This is QL minus Q. This way we can find out the rating. Do you have any doubt? Shall we start with questions?
Yes, sir. We should start.
Questions? Okay.
Yes, sir.
This is the first question. Which type of capacitors have similar effect as an overexcited synchronous condenser? Which one is the correct answer?
Sir, shunt.
Yes. At low power factor, a series capacitor produces less voltage rise than shunt. More voltage rise are equal or none. So what will be the answer here?
Sir, less voltage rise than a shunt capacitor.
Series will produce more. No, so series is primarily used for increasing the voltage. Shunt is mainly used for reducing the power losses.
Okay. Sir, why they have written low power factor?
So at low PF, R, we have this. So what is PF here? Power factor here is how much is it?
RYX. RYX.
Z.
Z.
So if R is almost same and but X is reducing. So X is increasing, not reducing. Then this will reduce overall.
Yes, sir.
So she series way, so directly it will R, this is JXL, it is JXC minus. So it is directly reducing the impedance. And also it is X, this is XL, X is NPTEL. This component is there for the series capacitor. Even if this word is not there, answer will be this. Correct?
Okay.
This is the third question. Three-phase round rotor system synchronous generation delivers a power of 0.8 plus 3.6 per unit to an infinite bus. It is like this. We have an infinite bus. Infinite bus means it is at one angle 0 per unit, and this is at the voltage that is at certain here. Na? Voltage is fixed at 1.0 per unit. Total synchronous reactance of machine and the connecting line. This is 0.85 per unit. Machine plus line. So it is proposed to add a series capacitor. So this is without series capacitor. Now we add one. This is 1 minus JXC. This is 0.85. So this is in this case x equivalent 1 is equals to 0.85. Here x equivalent, what is x equivalent here in this case?
So J 0.85 minus XC.
Yes. And it is said that such that maximum power transfer capability of the machine increased by 25%. So this is also in series capacitor is also used to increase the power transfer capability of the line. Because now X is reducing, so we can transfer more power. Because what is if we have two buses V1, V2, this is angle 0, this is angle delta, this is X. What is the power transferred here for this line from sending end to receiving end? Do you know this? Have you seen this before?
Yes, sir.
No. So here in second case, X is reducing. So overall power transfer capability is increasing. That is why here by using the series capacitor we want to do the same thing. We want to increase P the transfer capacity by 25%. So in first case this is P max 1. In first case it is here that and it is also called it is said that excitation is kept constant. So here this is E1. So this is E is same here. E angle delta. This is also E angle delta. So excitation is kept constant. So this values voltage terminal voltage for generator will be same. So we are only looking at maximum power transfer. So because excitation is same, here sin delta is also gone. We are only looking at maximum power because it is called, already mentioned here. We want to know only the maximum power transfer capacity. So P max is independent of the sin delta. So this is E into this is already 1. V V1 is E and V2 is 1. So E by X EQ 1. And this P max 2 will be same E divided by X EQ 2. But this P max 2 is 1.25 P max 1 because we want to increase the capacity by 25%. Okay. So now can you solve this question? How will you solve? You have these two equations. try to solve.
Yes, sir. First we will calculate P1 max.
So P1 is already given 0.8. This is 0.8. And second equation is this E divided by X EQ2, which is equals to 1.25 times of zero point 0.8. So now can you calculate XC? So how
Sir,
will it
1
XC you're saying 1? How?
X equivalent to is 1.
No, how? 1.
Magnitude of E is 1.
Magnitude of P or E?
E.
No, E we don't know. E we don't know. In this question, E is not given. So how can you solve? But we know that it is same in for both the cases. So either you take ratio of these two, or you equate E, or both is same. Both way you will get.
No. Then, sir, we can calculate this from XE1, like X equivalent 1 is given to us.
You can calculate that way, but that way you can do. This is known. It is 0.85. This is known. E you can get then substitute it here. But you can directly take ratio of these two equations, and you can write that xeq2 by xeq1 is equals to zero point 0.8 by 1. So xeq2 is zero point 0.8 times of xeq1. So how much is this?
Zero 0.68.
So how much is xc then?
XC.
Yes.
XC will be 0.8. No, 0.08.
No, no. How 0.08? This is xeq2, no? Second. This is equals to 0.85 minus xc. So how much is substituted here? Find xc. How much is xc?
0.6. 0.17.
Yes. So it will be 0.85 minus 0.68. So 0.17. So this is correct. This is in per unit. So capacitive reactance in per unit. Okay, clear? The same thing is written here also. Now this is the next question. So it is given that we have a star connected 440 volts. This is line to line volts. 50 hertz induction motor. Line current is given as 20 amperes at 0.85 lag. Then three ideal capacitors are connected in star fashion. Capacitors are connected in star fashion. To raise the power factor to 0.95 lag. So how much is This is theta 1 and this is theta 2. We need to find out the rating of capacitor bank in kVA. So, how will you do this question?
Sir, I will do first. I will find the active and reactive component of line current at 0.85 power factor.
Okay. Then
Then since load is same, so reactive component of current will be same in both case.
reactive or active?
No, active component, active only.
Yes.
Then we can compute the reactive component in second case 0.9 power factor lagging.
Yes.
Then we will calculate the capacitor current IC through the reactive current, both reactive currents.
How will you find IC?
IC from the reactive current, like let's suppose in first case reactive current was IR1 and in second case reactive current was IR2.
Okay.
Then whatever the difference between them, that will be IC, because that current we have to supply through the capacitor.
Yes.
And then IC we know, voltage we know, we
Yes.
can find out the kV rating.
Yes. You can find. Yes, you can do that way. So, so calculate how much are you getting. We also saw one other way, no? Using the power triangle. So you can do that way also using current, and this will become more easy. Indirectly, no. So this one is corresponding to, this is theta 1. This is theta 2. This is corresponding to 0.85. And this is corresponding to 0.95. And this is QL. Sorry, QL. And this is Q. So this is QC. So QC will be QL minus Q, right? Sorry, QC is QL minus Q. And how much is QL? PL we know. It is PL 10 theta 1 minus 10 theta 2. You know theta 1, theta 2, 10 theta 1, theta 2. PL also you know. So you can directly calculate QC.
Yes, sir.
So tell me how much is PL here? Calculate how much is
PL
PL.
will be root 3 times. So 15.24 2 kilowatt PL.
15 point yes. Okay, so now find out. So how much is this? This is 10 of cos inverse 0.85 minus 10 of cos inverse 0.95. So how much is this? Calculate this value.
Sir, 4.4249.
4.4 is यहाँ पे यूज करके आपको शामिल करना है is this correct? Is this correct? PL? Should be root 3 into VL into IL. And is this correct or we need to add something? Into 0.85 also. Root 3 will IL plus 5. So, power is not correct.
Yes, sir, it is 12.955.
Yes. 12.9 or 5. Now calculate this. How much is this? QC.
Sir, 3.76.
It's around 3.7677. So this is overall three-phase kVA rating of the capacitor. So next question is also continuation of this. Next is find the capacitance of each capacitor in microfarad. So we found QC as this 3.77 kV. So what is QC per phase?
1.253.
Yeah, so this is per phase. So it is given that capacitor is connected in star fashion, star connection. So we need to find out the
Capacitor current.
yes. What
IC.
how
Sir, it will be Q divided by,
you
I
can
think.
QC phase. How can you calculate this QC phase?
Sir, this will be QC phase equal to IC into V conjugate.
That is VI conjugate. That is S, and its imaginary part is Q.
Okay, okay.
For this, you need to calculate IC first. But can we directly calculate without using current? You can use this also. So for that, you need to calculate current first. So current will
Sir,
be
V square Y XC
oh yes.
Q.
So V phase by XC. QC we know. V phase we know. V phase is line voltage is 440. So it is, and QXC is 1 by 2 pi F into C. So this will be into 2 pi FC. So how much is C? which QC per phase divided by 50 hertz. Yes. So calculate this. How much is this? How much?
Sir, I am getting 61.98 microfarad.
It's around, say, it's around 62 something.
Yes, sir.
Okay, correct. We can also, using V into I also we can do. But for that you need to calculate current. For that again you will write V by XC. So directly we will reach it. So next is this question. So load is supplied by 440 volt 50 hertz source. 440 50 hertz. P and reactive power and active power consumed by load are such that P is between 10 to 12.5 and Q is 6 to 7.5. So an overexcited synchronous condenser at low load is connected across the load generators. So maximum power factor that can be observed across a load after synchronous condenser is connected. That you have to calculate what will be the maximum power factor achieved. So load ranges P and Q for the load ranges between, this is between 10 to 12.5 and this is between 6 to 7.5. So we need to calculate only maximum power factor. So which value will result in maximum power factor? What value of P and Q will give maximum power factor?
Sir, P max, Q min.
Yes, correct. Because P is P divided by, so we want this to be maximum. This can be maximum if this is maximum and numerator is maximum, denominator is minimum. So if you want this to maximum, this is also, it will increase. So only way we need to reduce this. So correct. So we need to take this value and this value. So how much is power factor? So so this is the load. Load requirement is 6 kVAR and the synchronous condenser is providing 5 kVAR. So resultant, how much is required from the source? How much will be required from the source?
Sir, 1.
Yes, 1 kVAR. So what will be the maximum power factor? Maximum. Okay, now I can directly calculate it. P is also known, Q is also known. So what will be P divided by?
0.996.
Correct. This is 12.5. This is 12.5. This is 1. This will be the maximum power factor. So leading or lagging?
So lagging.
Yes. So always mention whether it is leading or lagging with PF. Because if you simply write find 9968, it can be lead or lag. So unless we specify, we don't know. Okay. Options are not correct. So this is the next question. Next two questions are based on, three questions are based on this one. So it's a 4-bus distribution network with line data and load data given as follows. And base KVA is 1 MVA, then base voltage is 11 kV. So what is Z base?
One 121.
So we need to find out these impedances are given in ohms. We need to convert them into per unit first. The next is ideal compensating device injecting a constant leading reactive power of 160 kVAR is connected to bus 3 here. So bus 3 we are connecting one capacitor. Consider the bus voltage as 1 plus J0 per unit as the initial gas. Load in each bus is given as kilowatt and kVAR. So first of all convert them into per unit and then we have to solve the power flow. So which method we have to use here based upon the data which is given or initial condition which is given?
Sir, one method one.
Yes. So it is method 1. So if it was only this, only 1 per unit, then we have to use the method 2 because we only have the magnitude information, not the angle information. But here we know both. Okay, so let's calculate this per unit values first. So Z base we have found 121. Z1 per unit is let me copy this.
Sir, how much decimal value we should take during the calculation?
We'll take 4.
4.
Yes. Okay, so let us calculate this current value. Yes. So what will be Z1 per unit? Calculate. Divided by 121.
It will be 0.0219.
0.19.
One 0.00
8.
0.0019.
So I think there is some mistake. 6 plus this is 85. Please check your calculation once. Are you getting this?
'No, sir. In
This is
second term, I am not getting. Yes, sir.
this is 1.0235.
Okay. Okay, now it is correct.
How much is this?
0.0288.
Yes. Plus
0.009545.
9. Yes, correct. And then last one is Z3. How much?
0.00825.
25.
0.00373.
Yes. Now these are 1 MVA basis, so these are in kVA. So directly you can write P1 plus JQ1 is 0.25 plus J 0.2. Correct?
Sir, yes, sir.
And P2 plus JQ2 is 0.185 plus J and 0.165. And P3 plus JQ3 is 0.09 plus point. Okay. Now we have all this. So initial guesses. One angle there. So what should we do now? I think we have to do only one iteration. What was the question? What was the question here? The question is to find out the voltage at bus 3 after first iteration. Okay, so we have to do only one iteration. So how are we going to proceed now? We need to.
Now we will find branch current.
So for branch current, we need load current also.
Yes, sir. Load current, firstly we will calculate.
How to calculate load current?
Load current is the P2 minus JQ2 divided by V2.
Yes. Divided by V2 conjugate.
Yes, but angle is 0.
Yes, correct. So here it is only one angle 0, so directly one. It is simply P2 minus JQ2. Actually, these are all P2. This is P2. This is P3. This is P4. So this is 0.25 minus J 0.2. I3 is 0.185 minus J 0.165. And I4 will be 0.075. Okay, so now calculate I1. I1 will be sum of all the three. I2 plus I3 plus I4. So how much is this? Calculate. I2 is this is how much is this? I3 plus I4.
One is 0.525,
0 point
0.525
which is this one I1. Oh yes, 0.525.
minus J 0.46.
No, I think it is point. Calculate once. I think there is some mistake. Oh, 0.44 you are saying, eh?
So 0.45.
Oh, just a minute. 0.200. Oh, we have made one mistake now. So here we forgot to take the capacitor. So here one capacitor is also connected. So what we are doing is without capacitor. This is 160 kVAR. This we have to subtract from here. So this P3 will not be this. No? It will be 0.005 per unit. So now again calculate 0.005. Now tell.
So only at bus 3 power will subtracted.
Yes. So how much?
0.2. That is 0.3.
0.28. And I2
0.275.
yes.
0.08.
Yes.
I3 same as I4.
Yes. So now we know load currents, we know branch current. So how to calculate voltage?
V2 equal to V1 minus I1 R1 plus X1.
Minus I1 Z1. Yes. Calculate this. How much is this? Is one angle 0 minus I1. We know. And Z also we know. Z is 0.0288 plus J 0.0095. Yes. How much is this?
So 0.9822
99822.
angle 0.178.
Oh, one mistake. This I have by mistake I wrote Z2 here. This should be Z1. Calculate this. By actually I wrote Z2 here instead of Z1. It should be Z1. This will be V2.
So it is come out to 0.986 V1 angle of 0.097.
So now for V3, what should I write here? How to calculate V3?
V2
V2. V2.
minus I2 Z2.
V1 minus I2 Z2. Correct. So V2 is this one. No?
Yes, sir. I2 is 0.25. No, 0.275.
Yes. So this is V3 1. Similarly, we can also find V4 1. V3 1 minus is Z3. So calculate these values.
Sir, it is come out to be 0.977 angle of 0.172.
Angle is, I think, not correct. The angle will be 0.0881. Now we have to use this V3 minus I3 into Z3. This is Z3, I3. Okay, so from here we are getting V3 as this 0.977. If we remove this capacitor, then this voltage will be less than this 0.977. Because this will increase this value. So are you getting this value V3?
Yes, sir. Angle is this 0.081.
Okay, now calculate V4 also. Then we have to calculate the active and reactive power losses. We can compare this the same by removing the capacitor. So let us calculate first this voltage and then losses, and then we will calculate we will do the same question by after removing the capacitor.
So this I am getting 0.97.
Zero point 0.97
5
angle.
angle of 0.097.
Yes, this is correct. So now this now we have to calculate the active power losses in branch 3. So this is branch 3. So we know I3, I1, I2, I3 we have calculated. I3 is same as I4 and I4 is same as this 0.09 minus J.075. So what will be loss in branch 4, branch 3, active power loss?
So it will be I3 square R3.
Is I3 square I3. So how much is this? So this is P loss 3. How much is this?
0.00002.
This P loss you are saying?
Yes, sir.
Check once again. Calculate first magnitude of this I3. 0.09 square plus 0.075. So this multiply it by R. How much is this? Check this value.
Zero point zero 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 one 32.
0.0. Yeah, so this is in per unit. So we need to multiply it by 1000. So you'll get it in 1000. So we'll get it in kilowatt.
Sir, we will minus or plus. We will do minus or plus here
Here,
in magnitude calculation.
magnitude is always plus. Huh? Always plus. So this becomes 0.113 kilowatt. Okay. So now let us calculate reactive total reactive power losses. So we saw that one method how to calculate total losses. What can we do? We calculate PS and QS. Huh? QS calculate. How will you calculate QS? QS will be V into imaginary part of this. Correct? Or we saw that sorry, uh, I conjugate V is P minus JQ. V is 1. So P is
Sir, it's plus.
which one? This one?
Yes, sir.
No, VI conjugate is this, huh? P plus JQ. But I'm writing I conjugate V. So take conjugate both the sides.
Then it will be IV conjugate. IV conjugate, I think.
Sorry, correct. It will be IV conjugate, correct. Good. And so this will be minus of imaginary part of I. So I we have already calculated. Na? I1 is same as I1. How much was I1? So I1 is this 0.525 minus J 0.8. So this is 0.28 minus of minus 0.28. This is 0.28 per unit. So how will you find, now you know QS also. How will you find Total reactive power loss.
QS plus
QS.
QC.
QS plus or minus. Okay, QS ठीक है. QS plus QC and
minus QL,
minus QL.
that will be Kulos.
What is QL?
QL is 0.75, 0.075.
No, no.
No, no, no,
We are
no. Actually, we
calculating.
have to add all. Yes, sir, yes, sir. We have to add all the power.
So what will be this?
0.2 plus 0.265 plus 0.075. That will be 0.54.
No, this is 165.
Yes, sir, it is 1. Then it will be 4, I think. 0.75. That will be 0.44.
So how much is this?
That will be 0. That will be 0, I think.
Yeah. So what is the mistake here? Actually, problem here is this is we have taken only two decimal points. We need to take more decimal points here. If you'll take more for value of current here, this uh, imaginary part of current. Okay. So what you do? You know what is the problem here? What we are doing is correct. This is correct, but here because we are taking voltage as 1 per unit. Therefore, what we have to do is we have to calculate again I1, I2 and I3. Considering the voltages we have received here, we have calculated by A2, A3 and V4. Because here you assumed voltage as 1 per for calculating I1, I2, I3. That voltage is 1 angle 0, but we have already calculated the new voltages. So we have to use these voltages to calculate this current.
So first we have to calculate load current, new load current.
Yes,
Then we have to calculate branch current.
yes. So this is 0.986 angle. Okay.
Sir, generally in written exam, so lengthy calculation they will give or not.
Now for one iteration they can ask. They will ask. No, one iteration because here also in assignment. So you'll have to maybe only two bus system is three bus system is there. Here we are having four bus system. So maybe system can be small, but one iteration you can expect. So this you will have to practice. Otherwise, you will not be able to do in time.
Yes, sir. Sir, even in assignment, I am getting some wrong question as well.
Wrong answers.
Wrong, like, yes, I enter wrong question, wrong answers.
So you do calculation very carefully. Otherwise, there are very chances of doing mistakes are very high. So while doing questions, uh, check all the values very carefully. So you can directly add these things. For I1, we want only I1, and I1 is sum of all the currents. So you can 0.005 divided by voltage which we have calculated. V conjugate. 0.09 minus J.075 0.975. So calculate this. How much is this? So are you getting this? Are you getting this answer?
Zero point.
Let's verify this one, I1. If this is correct, answer will be correct. Some decimal points may be.
Yes, sir.
How much are you getting? Correct?
Yes, sir. Yes, sir. It is correct.
Okay. Yeah, so this is correct. Okay, if we start with this only, the I1, I2, I3 we have calculated here, then we will get loss as 0. That mistake we were doing. So in exam, keep this in mind. Okay, this question is go through this question again. And in assignment also you will find such questions. So do it carefully.
Okay. Sir, in this course, power system stability is not there.
Stability is not there in this course. So next we will study that load frequency control, and after that it is unit commitment.
Unit commitment means?
Unit commitment means, so commitment means that unit is committing to generate this much. So what we are doing that, let's say for the next day, in one day we have 24 hours, and each hour actually generators, how much they have to generate, they are told in, for each 15 minute they are given one schedule that you have to generate this much. So in one day there are total 96 time blocks, for one for each 15 minutes. 24 hours into 4.
Okay. 4.
So 96 time blocks. So if you want to know tomorrow which generator should generate how much, and how many generators should generate, so that overall cost of generation is minimized. So this is an optimization problem. We want to minimize the total cost of generation. Okay, so this will tell us two things. First of all, how many means at each at each time block the on and off status of generator, each generator. Let's say we have three generators. Okay, and let's say so for each time block we'll get the output. Let's say for time one we are getting this, that generator G2 should be off and only G1 G3 should be generating, and let's say the demand here is 100 megawatt. So now this 100 megawatt will be divided between G1 and G3. So how much they should generate, that we have to decide. So schedule of each generator. Each generator which are on. Okay, so it will give which generator should be on and for how much duration, and when it is on, how much should it generate. That is why it is called unit. And that means how much that generator has to, or each unit. Actually, let's say one generating station can have number of units. Unit 1, 2, 3. Overall capacity, let's say, is 1000 megawatts, and each generator is of 250 megawatts. So 250 into 4. So one plant.
Unit is nothing but generator.
So there is actually one plant, one power plant, one thermal plant is there, and in one plant there are four such units of 250
Yes.
megawatt each. Together they will produce, if
4 1000.
if they operate at their maximum point. And there are some constraints also, that minimum it has to generate this much. So those also we need to take into account while solving this problem. We will see how to solve this problem. There are different methods by which we can solve this problem. We can get this schedule. Or
Sir, everything has methods. Every problem solved to solve.
yes, you can calculate it. It's mathematics behind it, behind
Mathematics.
solving each and every problem.
Yes, sir.
Okay, so now you'll be able to do the assignment.
Yes, sir.
Okay, so any other doubt?
No, sir.
Okay, so then we'll meet next time, next Saturday.
Yes,
Okay,
sir. Sure, sir.
bye.
Thank
Thank
you,
you.
sir.